Today we will discuss about photoelectric effect. So it was Hertz during his experiments on electromagnetic waves observed a sparks in the air gap of his transmitter when ultraviolet light was directed at one of the metal walls. So the followers of this experiment discovered that the cause was electrons emitted when the frequency of the light was sufficiently high. This is known as photoelectric effect, and the emitted electrons are called photoelectrons. So Hertz observed a spark in his transmitter in his experiment when an ultraviolet light is directed towards one of the metal walls. But he didn't follow this experiment and didn't give an explanation for this phenomenon. And following this observation, many physicists came into field and experimented this, and they explained this as photoelectric effect. They said the followers discovered that the cause of this spark was the electrons emitted when a frequency of light which having a sufficiently high frequency is falling on the metal surface is causing to emit electron from the metal surface. So this is known as photoelectric effect, and the emitted electron is known as photoelectrons. So what is the experiment for this? So it is shown in the figure here. Experimental setup. Here this is an evacuated tube, and there are two metals connected here, and it is connected to a variable potential. Variable potential means a variable resistor is connected here, so the voltage can vary according to our need, and a voltmeter and an ammeter is connected in this circuit, and the one of this metal rod which is connected to the positive terminal, which is anode, is radiated with a light radiation. So this is the experimental setup. So when the metal plate, that is the anode plate, is irradiated with a light wave, some of the photoelectrons that emerge from this surface have enough energy to reach the cathode despite its negative polarity. So whenever a light of suitable frequency falls on this positive metal surface, that is this surface, electrons are emitted from this surface and it is moving towards this cathode. This is shown here. So the electrons will have negative energy and the cathode will have negative polarity. So usually by nature it will repel each other, but instead of this negative nature of this electrons and cathode, instead of this repulsion, some of the electrons will overcome this repulsion and flows in these circuits, so which contribute a current in the circuit, which we can measure using the ammeter in the circuit. The slower electrons are repelled before they go to the cathode. So only those electrons which having high velocity is reaching the cathode, that is the electrons which have energy to overcome this repulsion between this cathode and electron will reach the cathode. Other electrons will repel even before reaching the cathode. If we are increasing the voltage, our variable voltage, and reaching it to a value V0 of the order of several volts, what happens? No more photoelectrons arrive, as indicated by a current dropping to 0. So if we are increasing the variable voltage and reaches a value V0, we can see that no more current is detected in the ammeter. That is, no more electrons are arriving in the cathode. This extinction voltage corresponds to the maximum photoelectron kinetic energy. So, which means this corresponds to a value of maximum kinetic energy for electrons. So, if we increase the voltage beyond this value, no increase in energy can be detected for this electron. That means no electrons will move in this tube towards the cathode. So, this is the maximum voltage corresponding to the maximum kinetic energy of the electron. So, an explanation for this phenomenon was given at that time, which is the light waves carries energy, and some of the energy absorbed by the metal may somehow concentrate on individual electrons and reappears as their kinetic energy. So, what was the explanation? That is, the light waves which entering the or which falling on the metal have energy, and this light wave distributes its energy to the individual electron which is in the metals, and this energies are concentrating on these electrons, and the individual electrons acquires this or reproduce this energy as its kinetic energy, and it moves through the tube by leaving the metal surface. This was the explanation given for this phenomena. But following the experimental findings, we could see that such a simple explanation was not adequate to explain all the experimental observation of this event. So, first point is that within the limits of experimental accuracy, that is about 10 to the power minus 9, there is no time interval between the arrival of light at a metal surface and the emission of photoelectrons. However, because the energy in an electromagnetic wave is supposed to be spread across the wavefronts, a period of time should elapse before an individual electron accumulate enough energy to leave the metal. So, what does this mean? Since the electromagnetic wave is supposed to spread, because since the electromagnetic waves having energy and its energy is distributed across its wavefronts, when the light falls on the metal surface, there should be a time lag between the spreading of this energy from this wavefronts to this individual electron, and by acquiring this electron, the electrons should leave the metal surface. There should be a time lag between this transferring the energy from the wavefront to the metal surface and leaving the electrons from the metal surface. But during our actual experimental observation, we could see that there is no such time lag between this falling of light energy on the metal and leaving of the electron from the metal surface. So this was a one discrepancy find with the with our simple explanation of this phenomenon. A detectable photoelectron current results when 10 to the power minus 6 Weber per meter square of electromagnetic energy is absorbed by a sodium surface. So, an example is given here. A layer of sodium 1 atom thick and 1 meter square in area contains about 10 to the power 19 atoms. So, if the incident light is absorbed in the uppermost atomic layer, each atom receives energy at an rate of 10 to the power minus 25 watt. At this rate, over a month would be needed for an atom to accumulate energy of the magnitude that photoelectrons from a sodium surface are observed to have. So, according to this theory, this explanation given to this phenomena. If you are considering a sodium metal surface of 1 meter cube thickness, it will take over a month to leave the photoelectrons from the surface. That's what explains here. And the second point is, a bright light yields more photoelectrons than a dim one of the same frequency, but the electron energies remains the same. The electromagnetic theory of light, on the contrary, predicts that the more intense the light, the greater the energies of the electrons. So we could see that from experiments that when the intensity of light is very high, more number of electrons are emitted from the metal surface. That is, when the intensity of the falling light is very high, the number of electrons emitted from the surface is high, and when it is less, the number of electrons is reduced. But the energies of all the electrons emitted from the surface are same. But according to electromagnetic theory, this contradicts the fact that when the intensity of the light is more, the greater should be the energy of the electron. So this is another discrepancy we find. And the third point is, the higher the frequency of the light, the more energy of the photoelectrons have. Blue light results in faster electrons than red light. At frequencies below a certain critical frequency μ0, which is characteristics of each particular metal, no electrons are emitted. Above μ0, that is the critical frequency, the photoelectrons range in energy from 0 to a maximum value that increases linearly with increasing . This observation also cannot be explained the electromagnetic theory of light. So we could see that from experiments that whenever the frequency, the higher the frequency of the falling light on the metal, the more the energy of the photoelectrons will have. So if blue light is falling on the electrons, it will result in faster electrons. If red light is falling, slower electrons. So there is a critical value of frequency near 0, which is characteristics of each metal, above which no electrons will be emitted. Okay. Below which no electrons will be emitted from this metal surface, above which the electrons can have any energy ranging from 0 to a maximum value. This will this is shown in here. Frequency, this is shown in here. Okay. Now the quantum theory. So then comes a explanation for a suitable explanation for this phenomenon, which is the quantum theory of light, using the quantum theory of light. In 1905, Einstein realized that the photoelectric effect would be understood if the energy in light is not spread out over wavefronts but is concentrated in small packets or photons. Each photon of light of frequency nu has energy h nu. So we have explained the phenomenon of photoelectric using the wave theory. That is, we said that the energy is distributed across the wavefronts and it is imparted to the electrons of the metals. So it is not adequate, that is clear from our experimental observation. So Einstein introduced that a quantum explanation needed for this to explain. He said that the energy is concentrated not over the wavefronts but in small packets, which is called photons. So each photon of light of frequency nu has energy h nu, the same as Planck's quantum energy. Planck had thought that although energy from an electric oscillator apparently had to be given into electromagnetic wave in separate quanta of h nu each, the waves themselves behaved exactly as in conventional wave theory. So Einstein break with classical physics was more drastic. Energy was not only given to electromagnetic waves in separate quanta, but was also carried by the waves in separate quanta. This was very important in this theory also. So the three experimental observations listed above follow directly from Einstein's hypothesis. So according to the previous theory, we could find three contradictions and which could be solved by the quantum explanation of Einstein's theory. So the first point is, because the electromagnetic wave energy is concentrated in photons and not spread out, there should be no delay in the emission of photoelectrons. So we could see that there is no time delay between the falling of the light energy and the emission of the electrons from the metal surface. So it could be explained using the quantum theory. Since the electromagnetic wave energy is concentrated in photons, there is no time lag between this energy spread out and the falling of the leaving of the electrons from the metal surface. And the second point is that all photons of frequency nu have the same energy. So changing the intensity of monochromatic light beam will change the number of photoelectrons but not their energies. And we could see that when the intensity of the light is increasing, more number of electrons are emitted but the energies are the same. This can be explained using this theory that all photons falling on the metal surface have same frequency and hence same energy. So this energy is imparted to the electrons, hence all the electrons leaving the metal surface will have same energy. But when when the light falling on the metal surface very intensely, more number of electrons will be ejected out. And the third point is, the higher the frequency nu, the greater the photon energy h nu, and so the more energy the photoelectrons will have. That is, the higher the energy of the falling light waves, the higher will be the energy of the photoelectrons emitted from the metal surface. So we could explain all these discrepancies that we have observed or that we have found by explaining using the previous theory. Okay, so this was a suitable theory in order to explain the photoelectric phenomena. Now we will define a new term, critical frequency. So we have already defined what is this critical frequency, below which no photoelectrons will be emitted and above which the photoelectrons can have energy ranging from 0 to a maximum value. So there must be a minimum energy phi for an electron to escape from a particular metal surface, or else electrons would pour out all the time. This energy is called the work function of the material and is related to nu zero by the formula phi is equal to h nu zero. So whenever the light falls on the metal surface, the electrons should have a that is, there should be or there must be a minimum energy which is represented by phi in order to leave the electron from the metal surface. And this is characteristics of this metal and this material, and this is known as the work function of the material, and it is related to this frequency by the relation phi is equal to h nu zero. nu 0 is the critical frequency. So the greater the work function of the material means the more energy is needed for an electron to leave the surface. So the larger the values of the work function, the greater the energy needed for light wave to or the electrons to leave the metal surface, and hence higher the critical frequency for electrons photoelectric emission to occur. To pull an electron from a metal surface generally takes about half as much energy as that needed to pull an electron from a free atom of that metal. So if we are pulling out an electron from a metal surface and we are pulling out an electron from a free atom from its outermost shell, and the energy, if you are comparing these energies, the energy in the former case is just half as that of the second case. An example is given here. The ionization energy of cesium is 3.9 electron volt, but its work function is 1.9 electron volt, on just about half of this value. Since the visible spectrum extends from about 4.3 to about 7.5 to 10 to the power 14 Hertz, which corresponds to quantum energies of 1.7 to 3.3 electron volt. The photoelectric effect is a phenomenon of UV and visible region. Since the energy spread is in this frequency region, the photoelectric effect corresponds to UV and visible regions. According to Einstein, the photoelectric effect the photoelectric effect in a given metal should obey the equation H nu is equal to kinetic energy maximum plus phi, where H nu is the photon energy, kinetic energy maximum is the maximum photoelectron energy, which is proportional to the stopping potential. So above which the electrons will not be emitted, or the electrons will not have energy above this values. That's why it's known as stopping potential. And phi is the minimum energy needed for an electron to leave the metal. Since phi is equal to H nu 0, we can substitute this expression here for phi. So this expression becomes H nu is equal to kinetic energy maximum plus H nu 0. Kinetic energy maximum then can be written as H nu minus H nu 0, or H into nu minus nu 0. This formula accounts for relation between kinetic energy maximum and nu from experimental data. If Einstein was right, the slopes of the line so it is shown here. So if Einstein was right, the slopes of the lines should be all equal to the Planck's constant h, and this is indeed the case. So this is the graph. So if the Einstein's theory was right, all the slope of this graph, which here shown the graph for cesium, sodium and calcium, all these graphs should be equal to the Planck's constant. So in terms of electron volts, the formula is equal to H nu for photon energy can be represented as is equal to H nu. Here H is the Planck's constant and this is nu, and for the denominator value represents a factor which is to convert the energy joule from volt. If we are dividing this quantity by this quantity, this will convert it into electron volts. So this is the energy in terms of frequency in unit of electron volts. If we are given instead the wavelength of light, since nu is equal to c by lambda, we can express the energy in terms of wavelength as the energy in electron volt, which is this quantity, sorry, h this quantity, and c by lambda. So this is the energy in terms of wavelength. So this is about photoelectric effect.